So you're all seeing the slides?
Yes.
Okay, so today I'm going to talk about the paper that we had at KDD last year, Attacking Graph Neural Networks with Bit Flips, Weisfeiler and Leman go indifferent. And considering that this event today is called Graph Learning on Wednesdays, I assume you all know the basics of graph neural networks, etc. And Celia also has nicely introduced them already, so we are going to directly jump into the interesting parts. So classic attacks on graph neural networks are poisoning and evasion. Poisoning and evasion seek to manipulate the input graph through node or edge insertion or deletion, or through feature manipulation. They're usually gradient or reinforcement learning based, and they're rather well explored in the sense that there's a large chunk of literature that treats these kinds of attacks. Poisoning typically refers to the training time attack, whereas evasion refers to the inference time attack. On the right-hand side in the figure, you see an example of evasion through edge insertion. So let's say you have a graph G, and that is fed to an n-layer GNN, and to get some node classification by that GNN, like the ones and the twos, they are the classes here, and then an attacker would try to insert a malicious edge into the graph and obtain the graph G prime. And for this graph G prime, in a one-layer GNN, the red question mark nodes would be affected by this attack, and in a two-layer GNN, in this small example, the entire graph will already be affected. Now, bit flip attacks, or BFAs, are an orthogonal approach to poisoning and evasion. Instead of manipulating the input graph, they directly manipulate the model's trainable parameters. BFAs are typically gradient-based, and they usually target quantized models, as particularly integer quantized models are numerically more robust to parameter perturbations than their floating point counterparts. BFAs have been rather well explored for CNNs, as you can see here on the right-hand side in figure 5, that is. Since 2018, there has been an increase in interest in this kind of research for CNNs, and this trend also has progressed to the present date, but they are rather unexplored for GNNs. BFAs are always inference time attacks. Now, how do these BFAs work? A BFA attacker always seeks to induce bit flips into weight matrices of a target model. And typically, these bit flips are realized in hardware through row hammer attacks or derivatives of this attack. Now, on the right-hand side, you see an illustration or conceptualization of how such an attack on a GNN would look like. We have the input graph, in this case, it's potassium cyanide, and the GNN correctly classifies it as toxic. Now, this GNN has multiple layers indicated here by L, and these layers, they have some transformation matrix, and we're looking here at the W subscript IJ superscript L, which is basically a weight element of one of the transformation matrices that's occurring, and it's given here in integer 8 representation. Now, the BFA attacker will try to perturb this particular weight or any combination of weights in such a fashion that in this example here, potassium cyanide would be classified as non-toxic. The interesting question now is how, out of the millions of weight elements that you have, or millions of bits that you have in a GNN, how do you find the vulnerable bits? For CNNs, this question has already been answered. By Rekin et al., they introduced the so-called progressive bit flip attack, or PBFA. In PBFA, the attacker tries to optimize the equation that is given here. So in the equation, what do you see? You see that the attacker wants to maximize the difference between the classification loss of the model, the perturbed model on a given batch or sample of data, and the unperturbed model. The attacker tries to do this or optimizes this equation using what is called progressive bit search, or PBS. PBS consists of two components, the intra and the cross-layer search. In the intra-layer search, the attacker first uses gradient ranking to determine which weight elements in each layer and which bits are the ones that are most vulnerable in this layer. And then in the cross-layer search, the attacker finds out which bit concretely in the global view, in the entire network, is the one that will optimize in this iteration. It's an iterative algorithm, will optimize this target function most effectively. Now, why should we even explore BFA on GNNs if there is already a solution how to do this, if there's been already a lot of work how to do this for CNNs? Well, it can be shown that BFAs are non-optimal on non-CNN architectures. Let's shift our attention to figure 10 here on the right-hand side. And in the left graph that we see here, you see bit flip attacks on large convolutional architectures. And what you see here on the y-axis is the accuracy, on the x-axis the number of bit flips, and you see they degrade quite quickly. In the graph on the right-hand side, on the other hand, you see the same setup, but just for a simple MLP, a simple multi-layered perceptron. And as you see, the accuracy degradation per bit flip in the simple MLP here is much less than in the larger convolutional architectures. Now, these MLPs are also an integral component of many GNN architectures. Beyond that, GNNs also differ fundamentally from CNNs. They operate on graph data. They operate by the message passing paradigm, both of which is not present in CNNs. And for GNNs particularly, there are certain theoretical concepts that we can exploit, such as expressivity. To further motivate our research, we conducted a little case study. In our case study, we trained GATT and GCN on community-based tasks and GIN on structure-based tasks. And what we found, let's look at figure 8. You have on the y-axis the difference between pre and post attack model quality, and on the y-axis the number of bit flips in the log scale. The blue color is random bit flips, just uniform random induction of bit flips across the entire architecture. And PBFA, the red, the orange one, is the attack that we just discussed. And as you can see on the structural tasks, such as MOL-HIV or MOLTOX-CAST, where we trained GIN, we found that there's only a little bit of difference, even for very large numbers of bit flips. So we have here over 10,000 in the MOLTOX GIN case. The difference between random bit flips and progressive bit flip attack is only minor. Whereas if you look at the community-based tasks and GCN or GATT, we see that, for example, with PBFA, we can degrade GCN on Cora. We can get a difference of up to almost 0.7 with less than 10 bit flips. Now, the question is, why is GIN so resilient? And to answer this question, we first need to talk a bit about expressivity. Now, expressivity characterizes a GNN's ability to distinguish graph structures. This is typically benchmarked against the Weisfeiler and Leman isomorphism test. Now, the Weisfeiler and Leman isomorphism test is an iterative graph requiring approach whereby in each iteration, the node neighborhoods are injectively hashed, and for two graphs after a certain amount of iterations, if their color histograms differ, then Weisfeiler and Leman decides that they're non-isomorphic. Graph isomorphism networks, for which we have the message passing equations here, try to simulate this behavior. So if you look here at the first equation, you see we have first summation, which under certain constraints can be injective, so we can get an injective neighborhood aggregation. And then we have an MLP, which can also learn under certain constraints an injective function. And yes, for an injective readout, what we'll find is, or what has been shown in literature already actually, is that MLPs, if all MLPs that are present in GIN are injective on their respective input space, then it is equally expressive as Weisfeiler and Leman. Now, how can we use this to synthesize an attack? Let's look at the following. Let's consider the two nodes V and U here, and let's consider their depth2 unfolding trees. As you can see here, we will need to injectively map the node neighborhood given in the right-hand side branch here, and then injectively map again in the depth1 unfolding tree the two different neighborhood representations in order to obtain different embeddings for the nodes V and U. And if we take this to a graph level, then of course, in order to distinguish two graphs, we will have to be able to distinguish all the nodes which have different unfolding trees. However, there is a problem that we need to solve before we can use this to craft an attack. So the thing is, there exist certain graphs for which injectivity, if it would just target a randomly selected layer and try to degrade injectivity there, this injectivity could be restored. So the expressivity could be restored. So let's look at this graph here. And for this graph, if you look in the color scheme that we have here on the right-hand side, so we have a homogeneous initialization, then we have a function f1 that is injective based on the node neighborhoods, and we get this coloring in the second row. And let's say we have a perturbed function or a modified function f1 hat that gives us this coloring, which is non-injective for the different neighborhood multisets. Then it is possible for a function f2 hat to exist that still gives us the same output as we would have by f2 applied to f1. Now, to alleviate this problem, we propose the injectivity bit flip attack in our paper, which considers the whole network. So IBFA comes into variance, IBFA1 and IBFA2. Let's look first at IBFA1. So what we do is, in IBFA1, we have first an input selection step. In the input selection step, we try to find for a given sample of a data set the two data points that maximize the L1 or KLD loss between the outputs of the model. Once we have found these two data points, what we do is we perform PBS as described above to minimize this optimization goal here, which is the L1 or KLD loss, depending on the task type, for the perturbed model between these two data points. So the idea is to pick two data points that with respect or from the perspective of the models are very far apart, and then try to flip the bits such that the outputs become merged. Now, for IBFA2, it in principle works the same way. However, what we observed when we developed IBFA1 is that it might be possible that the solution to the input selection algorithm changes during the attack iteration. So what we do in IBFA2 is simply that we rerun the input selection after each and every attack iteration. For evaluation, we evaluated on the Open Graph benchmark dataset, or OGB, where we have molecular graphs and graph classification tasks. We also evaluated on the TU dataset, where we have social networks and graph classification and node classification tasks. As models, we trained GIN and GCN, and for quantization, we used integer 8 scale quantization, and we trained the quantized models using straight-through estimation. Now, let's look at the results. In the top row, you see the prediction, the average prediction quality over 10 runs in the y-axis, and you have different data sets here on the x-axis, and the colors indicate what kind of attack or model we are running. So we are running here, the red is the clean model, the orange is PBFA, the shades of gray are IBFA1 and 2, and blue is the random bit flip attack. And what we see, what I think is very interesting, so on all these molecular data sets, for a given number of bit flips, which we see in the bottom row, it's the average number of bit flips that we had for this attack. What we see in the top row is that on all these molecular structural tasks, IBFA1 and 2 can quickly turn the model into a random number generator, whereas the progressive bit flip attack does not significantly outperform typically the random bit flip attack. This is a stark contrast to the to community-based datasets, Colab and GitHub Stargazers that we had, where PBFA and IBFA mostly performed equally well or degraded the model equally strong. We also conducted an ablation study where we looked at the convergence towards the random output, the random predictions, as well as the layer preferences of the different attacks. So what you see here in the top two rows is the probability that a given layer will be selected for a bit flip on these different data sets. And in the top row, you see progressive bit flip attack, and in the central row, you see IBFA1. And as you can see, obviously, progressive bit flip attack has a strong preference for the input layer, so to flip the bits there, which makes also sense from a perturbation analysis point of view. To flip the bits in the input layer, it will give you basically the most bang for your buck. On the other hand, in IBFA1, we see that the distribution of the bit flips is completely different from PBFA, which I think nicely reflects the different optimization goal, the different approach that we have. Regarding the conversions towards randomness, in the last row, you see kind of expected that IBFA leads to a faster convergence or faster degradation of the model prediction quality. And what I personally think is very interesting, what I don't understand exactly why this happens, for the progressive bit flip attack, let's look at, for example, the lower left corner of the figure. We see that on mol HRV, it's a pretty strong signal here that we see that progressive bit flip attack can produce these patterns where it first degrades the model a bit, but then increases it. Surprisingly, I would not have expected that. So to conclude, we find that certain GNN architectures can be very robust to conventional progressive bit flip attack. We introduce the injectivity bit flip attack, which seeks to exploit the GNN expressivity mechanisms and which we show empirically effectively degrades GNNs. Open questions in the domain are, how can we effectively defend GNNs from such an attack? Is it possible, or can we effectively reconstruct a GNN after it has been attacked so that it verifiably matches its pre-attack state? And also, how do different quantization approaches, I mean, there is not only integer 8, you can do many different things, you also don't have to do scale quantization, etc. How do these different approaches affect the robustness? Thanks for your attention.
Thank you, Lorenz. Thank you for sticking on time. So now we can just split in the breakout rooms for a discussion where you can ask whatever you want to the authors. Thanks again, both to Celia and Lorenz, for the talks.